that gives us our much colder winters.
And then the tropical regions, which are in the middle part of the Earth, we see pretty much equal amounts of energy coming to us from the sun because they're almost always facing at the same angle.
The sunlight that comes through the atmosphere, some of that is reflected by the Earth. Not very much. A forest will only reflect 10% of the sunlight falling on it. Ice may reflect 60 or 70 or 80%.
And then that, in turn, is re-radiated as infrared radiation. And it begins to heat the atmosphere. That heat radiation wants to go back out into space. But there are certain chemical constituents in the atmosphere that are opaque to certain wavelengths of heat radiation. Chief among them are water vapor, carbon dioxide, methane, artificially introduced things like CFCs, all the things that we call collectively greenhouse gases.
And those gases, by absorbing that energy that the Earth's giving off, when they give it back off, it helps to warm the Earth and makes the Earth habitable as a planet. If those greenhouse gases weren't there, the average temperature of the Earth would be too cold to support life. When the energy coming to us from the sun reaches the top part of the atmosphere, it comes through a series of layers in the atmosphere, one of which we call the stratosphere. And the stratosphere is where we find a very narrow layer of ozone. And that ozone absorbs some of that radiation that's coming down. And as it absorbs it, it's absorbing the very short wavelength energy, the high frequency, the energy that's capable of breaking down the cells in your body, giving you skin cancer and so on. As the radiation continues to move on down, we get into the lowermost part of the atmosphere, which we call the troposphere. And the troposphere is where we live, where all of the weather takes place. So all of your storm systems, all of the blizzards that move back and forth, the hurricanes, they all develop in the troposphere.
The atmosphere is a dynamic system. It's actually an atmospheric ocean, coupled atmospheric ocean system, because these are two fluids. The atmosphere is a very thin fluid, and water, of course, is our familiar fluid, that absorb energy and then release it.
We know in the lower latitudes, in the tropics, it's really, really warm. And in the polar regions, it's very, very cold. So one reason why we have weather is to get rid of this imbalance.
So all other things being equal, the equator is going to be warmer than the poles. Well, you want to equalize that temperature gradient. Energy is going to flow from greater energy to lesser energy. So if you think of it as a gradient, it's always going to flow downhill, so to speak, from higher temperature to lower temperature.
Where warm air and cold air do get close to each other, warm air is lighter and it slides up and over the cold air. Well, the atmosphere is colder up above us, so warm air laden with moisture goes up, turns into clouds, and we get a storm.
So we get air moving from excess to deficit. And that movement of air across the Earth's surface is how we get winds. So if there's a lot of air here and a little bit of air here, you get a really rapid movement of air and you get really fast winds. So it's all pretty much interconnected.
Weather are the details of our climate, what happens on a day-to-day basis. And the things we think about there are the extreme events, the huge floods, the big droughts, the giant snowstorms. Those are the extremes of weather that happen when a particular set of storms or events, the jet stream, all come together and produce something that we think of as a big weather event. Now, the climate is something else. The totality of all the weather events that control how warm it is in winter, how extreme our temperatures get in summer. And when we talk about the changing of climate, we're talking about something else. We're talking about how that shifts with time. There are consistent patterns to the orbital changes. That is, we know what the Earth's orbit has been for the last million or so years that is associated with the Ice Age cycles.
There are 3 known cycles. The Earth rotates about the Sun in a nearly elliptical orbit, but the amount of ellipseness changes from being nearly circular to more egg-shaped to nearly circular. And that occurs on a scale of 100,000 years. The Earth rotates about an axis of rotation, which goes from the South Pole up through the North Pole. And that axis of rotation is tilted by 23.5 degrees currently, but it actually varies from about 24.5 to 21.5. And finally, the axis of rotation of the Earth wobbles like a top, and that occurs on the scale of about 41,000 years. So all these variations taken together will naturally affect climate and climate change. And things like variations of solar output affect climate naturally. It's a natural climate change mechanism.
One of the solar cycles that we've been familiar with, and it kind of started the study of the sun back in the 1600s and 1700s, was something known as the sunspot cycle. About every 11 years, the sunspot cycle reaches a maximum number, and then it goes back down to a minimum. In fact, there has been a great correlation in the past about 60 years with Arctic temperatures and the amount of energy coming out of the sun. And it actually fits a tighter pattern than predicting Arctic temperatures with a change in carbon dioxide.
The big change that has happened just in the last 2 or 3 centuries was the discovery of fossil fuels. First, the burning of coal to power steam engines drove the Industrial Revolution. Subsequently, we discovered oil and natural gas, and these cheap sources of fossil fuel have essentially powered the industrial development of the world in the last couple of centuries, accelerating just in the last 50 years.
And when you add additional greenhouse gases like methane, water vapor, carbon dioxide into the atmosphere, what you're doing is increasing the potential for the atmosphere to absorb radiation that's coming from the Earth and emit it again or give it back out.
The Earth's atmosphere is transparent to light. That means this sunlight, which is a short wavelength, comes through the atmosphere with only a small amount being absorbed, like 20 or 30%. Some is reflected by clouds, but when there's a clear sky, the rest comes through the atmosphere and is absorbed by the Earth's surface, unless it's reflected, say, by snow and ice. Only about half of what we are burning, half the carbon dioxide is being removed by the oceans and by forests. The rest is accumulating in the atmosphere, and the temperature of the Earth is inexorably with fluctuations going up, and that's pushing us towards a warmer climate. What is happening is that one key greenhouse gas, which is carbon dioxide, coming from the burning of fossil fuels, is going up rapidly. And we've had measurements now, very precise measurements of carbon dioxide in the atmosphere for the last 50 years. Steadily, it's been going up 2 parts per million every year, which means that in the last 50 years, it's gone up 35% in the atmosphere. And what that has done is take tens of millions of years of fossil carbon that had been taken out of the Earth 50, 100 million years ago and put it back into the atmosphere as carbon dioxide. The scientific community has known that we would face global warming for some decades now, but it's really only been in the last 10 or 20 years that the impact has been such that we can see it.
What's actually creating the climate change that we're observing in the last, say, 100 years? Is it the natural climate change mechanisms, or is it the human influence? 20 years ago, it was a legitimate debate in terms of whether actually we were warming or not, but that's been resolved. The last 10 years, the debate was, well, is it more natural mechanisms that are leading to the climate change, or are we having an influence? Today, I don't think it's much of a debate anymore. The overwhelming scientific consensus is that our human influence is affecting the climate of the world.
Almost all the warmest records in the last 150 years have been since the year 2000, all except one, and that one was 1998.
Another way in which humans have influenced climate is by some of the changes on the Earth's landscape itself. So, for example, urbanization. If you think about some of the larger cities, skyscrapers tend to be glass on all sides. What that glass does is it acts as a mini greenhouse. So it absorbs radiation in the day, and then it gives that radiation back out at night. So that cities tend to be warmer than the surrounding greener spaces are.
Scientists around the world are trying to understand how the weather will change in a warming world.
One way to visualize what is likely to happen to the Vermont climate is to look at how the Vermont climate might move across the climate zones of the United States as we move forward into the future. This diagram shows how the climate of Vermont will move across those climate zones as we go forward this century. What that means is that if we stay on our present path of driving our industrial society with fossil fuels, then the climate of Vermont by the end of the century will feel like the climate of northern Georgia.
And so there's a lot of work yet to be done, and especially because even if the temperatures for the globe are warming up and say will warm 2 degrees in the next century, that may not necessarily be the key factor in terms of humans dealing with any climate change. The key factors may be the fact that there may be a sudden drop in the temperatures for a decade around 2030. What are we going to do? And suddenly, you know, we can't produce wheat in the wheat belt of the United States for just 2 years.
We have a huge investment in the fossil fuel industry and in our entire energy infrastructure. You know, from power plants to automobiles to the whole energy industry itself.
We've discovered, you know, a century and a half ago, oh my gosh, we've inherited $1 trillion, you know, and we've been busy spending it like a drunken sailor, you know, on a spree.
So time is really running out. We actually have to shift our path from a high fossil fuel path to a low fossil fuel path as soon as possible if we're going to avoid major climate change by the end of the century.
So predicting climate on a general sense is an interesting exercise, but understanding how the climate changes in much more minute periods of time, that gets to be a more critical thing as we go forward, you know, trying to deal with any climate change. It only makes sense to me to be taking actions to reduce human impact on the environment, regardless of what the weather is going to do.
The development of the technology of the last century has given us huge benefits. The problem is that we did not foresee what some of the costs would be in terms of global environmental impact. How do we use the technology we have wisely? It's not something that an individual can do of themselves. It's something that requires real community effort. It requires a collective understanding and a political will to transform our society. It's certainly something we could do, and I'm certainly hopeful that we will do it.
I guess I'm not pessimistic about it. I think humans are much more adaptable than they might even consider themselves to be. But I find understanding those mysteries and getting deeper into what causes those changes, you know, I'm absolutely fascinated.
What we've introduced to you today are some of the basics of Earth's climate system. We've also heard Vermont scientists explain the immediacy of the situation, the obvious solution, and the urgent need for a climate-literate public. Let's hope that the combination of science, literacy, and America's uniquely innovative spirit will galvanize the political will and the positive change needed for a sustainable future, one in harmony with a stable climate. I'm Amy Seidel. Join me next time for more Emerging Science.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.